Second part of this unit, what you just took the quiz on yesterday, that had everything to do about angles, right? How to find an angle inside, outside, in between a circle, how to find all the angles. Now we're moving to, all right, I still have chords, secants, and tangents, but how do I find the lengths of them now? How long are they? I don't care about the angles formed anymore. How long are these chords, tangents, and secants? And yes, I am going to start off with a proof today, and this is a proof we did a couple units ago. This is a review. I'll throw some circle facts in the reasons column, but this is a review proof. Look at the proof statement for me. AE times BE equals CE times DE. We saw that proof statement a lot in this unit, and I'm going to have a few of you dig deep right now and see if you can remember what unit we did that in. When did we prove two line segments multiplied together equal another pair multiplied together? It was in a huge unit for us. Anybody remember the unit?
I have all the package.
It was similar triangles. Everyone remember product of the means equals product of the extremes. That's what we're doing. But again, going back to Lazy's point, you can't do that unless the triangles are similar. So let's do that right now. Let's first prove the triangle's similar. There are three methods of proving triangles similar, but when we do a proof, there's only one main method, and that is? All right, so you guys now are on the clock. Can you find me two pairs of congruent angles in those triangles? Find the first pair. I'm sure that's not a big deal, I think. 17, one pair you are confident in are congruent.
CEB and AD.
Yep, because they're what? There you go. So let's start there. Angle CEB congruent to AED. Vertical angles are congruent. So there's one pair of angles. Now the second pair is going to be a circle fact. And hopefully it's still fresh in your mind from yesterday's quiz. The next pair I'm going to get comes from a circle fact. Bless you. Give me another pair that's congruent up here. 4.
Angles that are like at the same arc congruent, and so CBE is congruent to ADE.
Say those angles again.
CBE is congruent to ADE.
Okay, I'm just going to put B and D for right now. B congruent to D. I could also write down C and A for the same exact reason. And I like what you said, but put a name to those angles that you said. What type of angles are B and D? They're in the circle. Inscribed. So here you go. Inscribed angles drawn to the same arc are congruent. Now I have angle. So go ahead, write the two triangles are similar. Make sure you use the tilde, not the congruent symbol. CBE, similar to ADE. Angle. All right, but now step 5 is not my proof statement. There was a step in between that I needed to write. Let's see if we can dig deep for that. What's going to be the reason for my proof statement when I eventually write it again? Product of the means. Well, you need those. Where do I find means and extremes? Where are means and extremes built into already? They are built into proportions, right? If the triangles are similar, their sides are in proportion. So that's our next step. All right, what sides do I fill in? The sides in the proof statement. But where? All right, AE you can put anywhere you want. So I'll put it in the top left. But if I put AE there, BE has to go in a certain spot. You don't get to put BE anywhere you want. So where does BE have to go then correctly? And remember, this is a proportion. How do you solve proportions? Cross multiply, right? So AE times BE, where would BE have to go then? 25? What's across mean? Bottom left, top right, bottom right. Bottom right. Because if I'm going to cross multiply, that's where it goes. And the other two, pick wherever you'd like. I'm still going to end up cross multiplying them. Ooh, what was the reason why that's true? How do you remember that? After angle, angle. CSSTP. Corresponding sides in similar triangles are proportional. Yep. And now, go ahead. Now tell me your means and extremes are equal. AE times BE equals CE times DE. Product of the means equals product of the extremes. Yeah, it was great doing a little review proof, right? We got a Regents at the end of June, but I didn't want to do this just to review similar triangles with you. This actually is our new circle fact today, which is, what are CD and AB in my diagram? Line segment CD, line segment AB. What do I refer to those as in the circle? 8. Those are chords. And they're intersecting, aren't they? So here's how my theorem today is going to start. If two chords intersect, that's true, but I don't want to write that's true under there. All right, that's true. What do anybody, a little math trivia? What do I call the answer to a multiplication question? I call it the product. Yes, so if the two chords intersect, product of their parts are equal. So going back up to my diagram before we put numbers with these, ready? If two chords intersect, ready? Part times part equals part times part. Good? All right? Everyone good there before we put numbers to it now. So we're not talking about angles anymore. We're now talking about lengths. All right, let's put that theorem to use. This first question, everyone see two chords in that diagram. They're the only two line segments. Everyone see they intersect. All right, tell me the product of two parts of one chord. So everyone look at one chord only, and somebody tell me the two lengths of the two parts. 17?
2x.
Okay, well, yep, you're fine. I just want to go a little slower. 2 times x. Everyone see those two parts? Equals the product of those two equal the product of the other two parts. Tell me what the product is of the other two parts. 13? Well, before you got there, though, back up for me. 8 times 2.5. There we go. Everyone see now how the theorem works. You just proved it true by doing the proof. 2x equals 20. Yep, x equals 10. Little basic intro problem before I step it up on you. Anybody all right? Confused with this theorem? Because it's going to go up in difficulty now, the problems. Oh, looks like we're going to have to draw our own diagram for number 2. Just a heads up, I'll remind you again tomorrow, though, Monday and Tuesday, you need your compass in class. We're doing our last constructions of the year. And congratulations, you're all done with proofs as well. If you've completed quiz 2, no more proofs until we review for the Regents. We are done. All right, what are we looking at here? AE is 3, EB is 16. All right, we've been down this road before. What are you putting on RE and ES? Not 3 and 4, but 3x and 4x. My diagram not drawn to scale. All right, give me two parts to multiply together. 14, two parts to multiply together.
4x.
Oh, yeah, we're going to see if I got any algebra studs that can handle that in a second. And how about the other two parts I'm going to multiply together here? Oh, 20?
3 and 16.
3 and 16, yep. which I know give me 48. Ooh, how about that left side, huh? I got a bunch of answers last class. I got 12x, I got 7x, I got 7x squared, all of which are completely wrong. 12x squared. X times x is x squared. And then everyone got all crazy. We take the square root of both sides. No, you don't. No, you don't. You don't take the square root of anything until the squared part is by itself, which is not. I got a 12 attached to that. So can you detach the 12, please, by 22? Yep. There you go. X squared equals 4. So we get x equals 2, but you didn't answer the problem for me. I didn't care about x. I was looking for the lengths of RE and ES. So take your 2, substitute back in. 7. What's the length of RE? 6. ES. Oh, we're ready for that one, huh? 8. Thank you. And that does check, right? 6 times 8, 48, equals 3 times 16, 48. Yep, we're good. All right, good. I thought I dropped the ball there. Any issues before we get to some honors level 1 here? Maybe not, but we'll see. Here's where this theorem starts getting a little confusing for a lot of students, is when I now, instead of a chord, I put another type of chord in there, a diameter. Remember, diameter is a chord. So hey, on number 3, do you see 2 chords that intersect? Yeah, it's just one happens to be a diameter. Let me highlight these 2 bad boys here. I got chord CD, and I got diameter, aka a chord AB. So they intersect. Part times part equals part times part. Let's label what we have. The chord is 3 centimeters from the center. Can you put a 3 somewhere for me, please, on your diagram? Where's 3 going to go? Hopefully you put it right here. And I got a radius of 5. So find a radius and put a 5 there. Can you put any more detail to my diagram? You know any other lengths up there? Yeah, the part from, what is that, A to the right angle is 2, because the radius was 5, right? More detail. I said you wouldn't be tested on it. I didn't say forget it completely, what we've been doing these last 2 sections. What else is happening there? John?
It's bisected.
The chord is getting bisected, right? Diameter perpendicular to a chord bisects it. That's still there. All right. Let's take chord AB is broken up into what part lengths right now? Give me both the lengths of the parts of chord AB. It's broken up into 20.
2, 8.
2, and then the rest, 8. Yep. And then look at chord CD. Nothing's labeled, but since I know both the same, I can call them both X or Y or whatever letter floats your boat. Yeah, X equals 4, but I was looking for chord CD though. The length of chord CD, 24. 8, double it. Again, diameters are chords. You understand? Oh, I really get this theorem. I really get it. And then I throw something that is a diameter in there that's also a chord. We go crazy. All right, how about 4? Do you see 2 chords? Do you see 2 chords intersecting? Yeah, here you go. I like to highlight them here. So there's a red chord right there, and then up another diameter. There it is. All right, let me start with the easier part first, the red one. The red one's broken into what 2 parts? 6. How long are the 2 parts on my red chord up here? 8 times 10. All right, let's go to the diameter now. The diameter is broken up into, we can all agree, x. We can all agree there. Ooh, hoo. How about that other part? Huh? How about that other part? I'm going to put that bad boy in yellow right here. How about this part right here? That's the other part I got to plug in there. Ooh. Well, I threw that 12 up there. The 12's what? That's a radius length. All right. If the radius is 12, how long is that diameter in the diagram then? Double it, 24. Isn't that whole diameter 24? And we already know one piece is x. And I'm looking for the rest of it. Just think about that. The whole diameter is 24, double the radius. This piece is x. So this yellow piece you can write as 17?
24 minus x.
Good. I don't know what's coming. Do you know what's coming at you right now? 80 equals 24x minus x squared. You know what's coming up here? Anybody know what's coming up? Yes, Kyle, say it with pride. Factoring, yes. Now, first, how do we even know factoring's coming up? Anytime you got an x squared, and just an x, it's time to factor. Again, if you just had x squared, I could take the square root of both sides. But when I have an x squared and an x in the same equation, yeah, you know it's factor time. Darn right. We don't factor anything unless, yeah, it's equal to 0. I know a lot of you, including me, it's a lot more convenient to bring over the 80. But then I'm going to get nervous because I would have a negative x squared, and I'm not too sure how to deal with that. So I'm going to take a little bit more work, and I'm going to move everything over to the left side. So my x squared can be positive. I get negative 24x. The 80 remains plus 80. All right, play around with the numbers. Just so you're playing around with the right numbers, you're looking for two numbers that multiply to, which one? 24 or 80? 80, the C value, yep. Play around with them, find them, don't give up. Find those numbers. 27, find them. 20 and 4, both have to be negative. X equals 20. X equals 4. We always have to be worried, though, especially when I get two answers. Maybe one won't cut it. And usually we just look for negative answers, right? And that probably doesn't work because I can't have a negative side length, but they're both positive. And I look at the diagram. One's not going to cut it for me. One of those answers won't cut it. And not because it doesn't look like it either. Okay, one of those answers isn't going to cut it. What was the radius length in this diagram? 12, right? So how in the world can x, which is part of the radius, be more than the radius, right? Everyone see why I'm about to reject 20. Not because it looks like it in the diagram. If the radius is 12, part of the radius can't be bigger than 12. So, see ya! It's gone. X equals 4. Whew. All right, got through that one. Last thing I got to do with you today. I didn't know where to put this theorem because it certainly didn't belong in the second section with all the angle facts. But since we're dealing with chords today, I felt, hey, why don't I put it in with a chord day? Because it does involve a chord. And here's what it says. Hey, you got two chords. If they happen to be parallel to each other, if you have two chords that are parallel, you know what? The arcs in between have the same measure. That's what this theorem is saying. Two parallel chords, the arcs in between them have the same measure. All right, that's it. Important fact. I felt like it was best to use it today. So two chords are parallel, arcs in between have the same measure. I'm going to do the first one with you, and then you're going to do the second and third one in your groups. All right, AB parallel to CD. Using my new theorem, what is now true? 5? CA and DB, same measure, Claire. Good. Okay, so I know they have the same measure. Let's keep looking at this diagram. 7, what is COD in this diagram? No, it's not. COD. A diameter which breaks the circle into 2 semicircles. So everyone good that now that COD is a diameter, this is a semicircle which measures 180. So 180 minus the 80 I already have, divided by 2 because those two arcs are congruent based on my theorem. 50 degrees for arc CA. All right. All right, you and your group, see what you can do with the last two. See what you can do. I'll write my work up here.
So it's going to be the same. So it's just the same.
All you have to do is add these, subtract it from 360, and divide it by the Haven't you torn it before?
Yeah.
No. That's not like you did. Yeah, no, of course not. Pour it down. But 140 was it's already 6 again. Yeah, we're gonna take out no. Well, take it out. What is snipping it? You're right. You got it. 210. Oh no.
Oh. So mine's 12 times 3. Minus 6.
Oh my god.
Okay, we should be having 140 and 125. Oh, good there. Okay, before I let you go and get going on the homework,